So now we use this entropy to prove some theorems about graph. So let's define what graph homomorphism is. So, okay, before that, let's say that we want to, first aim is to count the number of independent sets in G. So let's say G is a graph, and I of G is the number of independent sets in G. Okay, independent sets are the number of vertices which there are no edges between. And we want to count how many are there. So for example, if you have a complete graph, the number of independent set is m plus 1 empty set and each one vertex set. And for other graph, it could be different. And in general, if you have a more edge, then there are less independent set. And if there are less edge, then there are more independent sets. And we want to measure this in terms of the number of edges, but let's focus on, we will focus on the, deregular graph. Anyway, so let's keep in mind that's our goal. And let's say a map pi from a vertex of G to vertex of H is a graph homomorphism. If we have, so if all the edges are mapped to edges, so for example, if you have a graph looking this way, then let's say this is red. No. If we map this to here and this to here and this to here and say this to here, then what does this map to? This map to this. This vertex goes to here and this vertex goes to here. And this edge maps to, again, here. So edge maps to here. It's okay. So far it's okay. But now this maps to what? This to here and this to here. So this maps to here, which is not an edge in H. So in this case, this is not graph homomorphism. In order to make it graph homomorphism, you actually have to map this to here. Then again, this purple one maps to here. So edges maps to edges. We don't care how non-adjacent pairs are mapped to what. As long as as long as all the adjacent pairs are mapped to adjacent pairs, it is a homomorphism. So that's the definition, and we write homomorphism from G to K to denote the set of all graph homomorphism from G to H. So, as we saw in the example, it doesn't have to be injective, it doesn't have to be bijective. Several vertices could be mapped to the same vertex, and several edges could map to the same edge. So this homomorphism, this concept of homomorphism is very useful in many contexts. For example, this H could be a graph with a loop. Let's say you have H. You have B0 and B1, and you have a loop here. And let's say you have a graph Then let's say you consider some homomorphism. You map this here, then this has to be mapped here. And in order to preserve these two as an edge, this has to be also mapped to B1. Now, because of the loop, B1 and B1 are adjacent, so this edge can be mapped to here. And let's say this maps to here, and this maps to here. Then, what's the pre-image of this? So there is a loop here, so its pre-image could be anything. But this does not have a loop, so its pre-image must be two vertices which are not adjacent. Must be more than, it could be more than two, but that actually corresponds to a set of vertices which doesn't contain edge inside. So an independent set. And complement of independent set, whatever that is in this case, there could be an edge between, and there could be an edge between this set and then outside, so rest of them goes here. So it's actually easy to see that the set of homomorphism from G to this graph has a bijection, so has a natural bijection between the independent sets and this homomorphism. So number of independent sets in G is same as the number of homomorphism from G to this looped simple graph. And also, if you consider, say, K sub Q, then this has a natural bijection to number of proper Q colorings. Because if you have, say, K4 here, then you have a homomorphism between G and here, then all the pre-image must be independent, all the pre-image must be independent, pre-image must be independent, all the pre-image must be independent. So, each homomorphism corresponds to a partition of this graph into 4 independent sets, which is exactly the same as proper coloring, proper ball coloring. So, these are the few instances where this homomorphism is important. There are much more various applications to other concepts of graph. And one of the theorems that we want to prove is this theorem by Khan. If G is an n vertex, deregular bipartite graph, then what we have is the number of independent sets of G is upper bounded by the number of independent sets of K, TD, 2D, and over 2D. So roughly what it means is that among all n vertex bipartite graph, which is deregular, the graph which has the most number of independent sets are disjoint unions of KDD. So n over 2D disjoint unions of KDD. Let's just assume that n is divisible by 2D, although the above theorem holds when, even when n is not divisible by 2D. So what's the number of independent sets here? You choose one independent set here, and you choose one independent set here, you choose one independent set here, you choose one independent set here, then all together yields an independent set. So you simply take this and then you multiply them, then this gives us the number of independent sets here. And this is number of independent sets here. So this shows that the number of independent sets in a deregular bipartite graph is maximized when this is disjoint union of KDD. And we will prove this using entropy. But we will actually prove a bit more general statement. Let G be an n-vertex deregular bipartite graph. And let H be a graph with some possible loops. Okay, then what we want to show is that the number of homomorphisms from G to H is at most the number of homomorphisms from KDD to H to the n over 2D. So if we let H be this graph, then this becomes number of independencies in G, and this becomes number of independencies in KDD. So this theorem is more general than this Kant's theorem. And so it suffices to just prove this. So how do you want to prove this? We want to use entropy. And for entropy to prove some combinatorial object, what you do, you choose something in here uniformly random. That gives us random variable. And that random variable's entropy is same as logarithm of size of this set. So if we measure that entropy, then we know the information about the size of this combinatorial set. So that's roughly what we will do. So let's say we consider the vertices of G as just index, and we choose pi uniformly at random. So roughly what we want to do is we want to use the assumption that G is a bipartite graph, deregular n-vertex bipartite graph. Yes. So roughly intuition is that if you have some vertex, so A, B is a bipartition of G. If you have some vertex B here, and if you know its neighbor, and on this homomorphism, so we have to decide, so H has some vertices here. We need to decide whether, where does this we embed to? So we map this to here or here or here. But we have to map it so that it becomes a homomorphism. So it's depending on where does this guy is already mapped to. Once this mapping is fixed, then we have a choice for this to go. And similarly, let's say you have other here, which are also determined by, anyway, so let's forget what I just said. So in this way, once this is fixed and you have this, and where does this go to? The entropy altogether, they actually upper bound the entropy of this pi. This pi is determined by the each, random variable. Where does this go? Where does this map to? Where does this map to? The pi of say p is a random variable because pi itself is a random variable. So roughly, why KDD is maximized is that the Once you fix this, then choice of this and this and this and this and this are independent. But how do I explain it in more intuitive way? Is that we have to also use shearers to actually get into this situation. Yeah, maybe we just start the proof and then see, what kind of intuition you can have from the proof. So anyway, so our goal is clear. We choose this uniformly random, and we will consider the entropy, and that entropy is, we know exactly log of this, and we want to upper bound this. So for given this phi, let x be the x1 to xn, where each xi is pi of I. Then, as this is uniformly chosen, the entropy is exactly the same as the log of the number of homomorphisms. And let A union B be a bipartition of G. Then what do we have? This entropy of X is same as, let's say, for each C subset of vertex set, let X sub C be the collection of xi, joint distribution of xi, where I lies in C. Then this is nothing but xa joint distribution of all xn xb, which is you add xa and you add b, conditioning on xb. This is chain rule. So what do you know? G is a deregular bipartite. Then each vertex in A has D neighbors in B. So by using Schiller's lemma, what do we know? This is, this times D is at most if you sum over all B, give me a moment. Yeah. So if you use the Schiller's lemma, then what do you get is that the D times H xa is at most summation of H x neighbor of B, where P is in B. You have A, you have B. Each of B, you take the neighbor, take the neighbor, take the neighbor, and the information on here, you count them, then every vertex here is counted D times at most. So if you use this on here, then what do we get? Hx is at most 1 over D, and you add all entropy of X neighborhood B plus this. And this is nothing but you just add all, H of xb, AA. So you actually get the inequalities. This and this inequality is clear, and this inequality is here. So you get this inequality. So let's write it this way: 1 over d and summation of p of b, h, x, and b, plus summation of p in b, t, h, x, b, x, and b. So now what we want to do is this d times xb, assuming its neighborhood. So assuming something happens on neighborhood, now you have this b, and you add d times. What we want to show is that if we have this 1b and then you count entropy and multiply d times, then what we want to do is we replace this to the situation that we have copies of b, the fake b, so artificial b, d of them you add, and you have this. Then, given this, how you map it, those are independent. So what we wish is that we somehow use this and you convert it, you upper bound it by the homomorphism inside of KDD. So you have D term, so you have 1B. But this is the summation of D of these terms, and instead of this B, you consider the identical vertices, and you want to reduce this situation into this KDD. So that's what we want to do. Sorry, and I forgot to mention something. So this is XA and X and B, right? So that's actually dropping condition. So this actually assumes everything on A, and this only assumes neighborhood of NB. So this is bigger or equal. So we get this inequality. And focusing on here, this situation more resembles the KDD case. So now we want to estimate each of these terms. So we forget this for now. So we fix B, and we want to estimate this as well. So we fix B, and then we estimate this term. So let xp1 to xpd be the new artificially we add independent. So they are all independent random variable which have the identical distribution to this xp. So xp has some distribution. Of course, this xp is dependent on x. But we consider the other distributions which are independent, and these are also independent from x. They have the same distribution as xp, meaning that this xp is with a random, it's a vertex in H. And it has a probability that with certain probability it is this vertex, with certain probability it is this. You have the probability. This also has the same probability as that. Moreover, okay, so let me correct slightly what I said. So each of these has an identical distribution of this, and they are independent. But when this is given, so in a way that the P1 X and B has the identical, this has the identical, assuming this you consider the distribution, and assuming the same event, the distribution here are also identical. But once you assume this, they are independent. So that's the setup. You consider such distribution, then the entropy of X and B plus D times entropy, conditional entropy of XB conditioning its neighborhood is nothing but this, because each of XB and each of this has the identical distribution. So what I said before is wrong in a sense that this is also dependent on, 김명훈, how do I say it in a more rigorous way? Yeah, let's just say that okay, this has the same distribution as XB, assuming on the when you condition on certain event on here, this and this has the same distribution. And of course, because of that, even if you don't condition on this, they have the same distribution. So D of this sum can be rewritten in this way. And because now all these I are independent, all these D random variables are independent by our construction, this is nothing but the joint distribution. And here together, what we get by the chain rule, this is you take this T plus 1 random variable. So, but what is this? You have NB, D vertices, and B is adjacent, and B is adjacent, B is adjacent, B is adjacent. And this indicates which of these vertices map to H and which of this map to H, how does it map to the vertices in H. So the joint random variable XNB, XP1 to XPD is the random homomorphism in H homomorphism KDD to H in a certain distribution. So this is a finite set, and there are more than one way to actually give a distribution on there. So before we chose here pi as a uniform choice in here, but here you see, because of the previous choice, this has certain distribution. We don't know what distribution is, but on this bigger G, we have B and these vertices. Pi is chosen uniformly at random, and if you focus on here, then these vertices has a certain distribution. For example, if we have this H and this G, 1, 2, 3. Then if you choose a uniform random map, then this is A, B, 1, 2, 3. Then all possible way is that you send everything to B. You can actually count the homomorphism, or you can send 1 to A and 2, 3 to B, or 2 to A, B, and A, and 1, 3 to A, B. So you have a 5 homomorphism, right? So you choose one of them in random with a probability 5. But what's the distribution on N2, which is on 1, 3? If you consider a distribution here, then if you choose this 1, 3 is either BB, AB, PA, AA, but now this out of 5 choices, this happens with the probability BB, 2 over 5, and this happens with 1 over 5, this happens with 1 over 5, and this happens with 1 over 5. So this in here is now having some distribution, and according to that distribution, each of them has identical but some distribution. So this actually in here, if you see 1, 3, then here we have 2, and let's say P1 and P2. And according to this distribution, you map it, and then once it is mapped, then now you decide where these two mapped. If both of them are, say, AA, then it is mapped to B. Both of them are, BB, then this could be mapped to B or could be mapped to A with, 2 choices. So anyway, so now you see that this is some distribution which we obtain from this choice. And we choose this. So this is some certain probability distribution on the set of homomorphism from KDD to H. So you have this D vertices, which is NB. So this is a distribution of how to choose the image of these vertices. And then once you choose that, now this, you choose the image of this. But what's the entropy of this distribution? The entropy of this possibly non-uniform, probably non-uniform, but possibly non-uniform distribution is upper bounded by what do we know? So this is some certain probability distribution on here, but that entropy is maximized when this is uniform. So we know that the h of x is at most the logs of s, where x has a values in s. So that's the first thing that we have proved. This is upper bounded by log 2 of size of homomorphisms from KDD to H. So what do we have? This is log 2 of size homomorphism KDD to H. Then what do we have? So from here, if we apply this, then let's move this to down. Then again, this was 1 over d, summation of p in b, and the thing inside was almost log 2 of homomorphism of kdd to h. And how many vertices here in B? In B has half n vertices. So this is n over 2d log homomorphism of k td h. And that's upper bound of this, which is this. So you take the log, exponential 2 to the power of this entropy on both sides. Then the number of homomorphism of G into H is at most number of homomorphism from KDD H to n over 2D. This is what we get. And we can conclude that the number of independent set of G is number of independent set in KDD to the n over 2D. This proves what we want. So next time we will see one more application of this entropy, and we will see how one can generalize this. Generalize, what I mean is that here we have in Kant's theorem we have this condition that this is bipartite graph. Then what if this is not bipartite? So if we delete this, then would it be still true? So that's also what we will do in next video, or maybe next video. Yeah. Thank you.